Hello everyone, I will be presenting our recent work on characterizing the effect of slippage for active eye tracking. This is a collaborative work between UNR and Bates College, Dr. Michelle Green. Throughout the past year, we have been collecting visual experience database, a large-scale effort to create eye movements data and also head tracking in space. And this is happening, as you can see, across different range of environments, tasks, and a diverse group of participants. And we believe that this is a very helpful data set because it will allow us to study the underlying mechanisms of head and eye movement and gaze behavior in general in a more real condition where the participant is active. Here you can see me biking and making sure that the quality of the gaze tracking is going to be valid across the data collection. And I guess it's no question for this audience that this is not an easy problem, especially when we are dealing with different head sizes and different ergonomics factor for a wide and large group of participants. One of our talented graduate students, Bharat Shankar, came up with the design of two head rigs, the hard rig and the soft rig, shown here in this figure. And using 3D printing technology, we put together the world camera, the T265 head tracking module, and also the eye tracking device. This hard rig uses a ratchet mechanism, so it sits tighter and less comfortable on participant's face compared to the other one that we refer to as soft rig that uses an elastic rubber band originally designed for camera and GoPro applications basically. And each of these two designs have certain range of comfort, rigidity, versatility for different head size and weight. And we all know that the problem for active eye tracking is slippage, where the eye camera physically shifts on participant's face, causing error for gaze accuracy. Therefore, we design a data collection procedure where we calibrate first the participant standing over a treadmill, and then we ask them to walk and fixate at the center of the checkerboard pattern. At the end of the walking session, we validate the accuracy of the gaze tracking, and we basically repeat the same procedure over three different speeds: slow, medium, fast, 1.8, 3.1, and 4.2 miles per hour. Just to get a sense of what the size of the fixation pattern is, each of these square roughly subtend 1.6 degrees of visual angle designed by Brian, the stimulus presentation code. And this will give us a flow or value for gaze tracking error that we would expect in the next few slides. In terms of the metrics, if we draw and if we plot the gaze accuracy versus time, cyan here shows the gaze accuracy in the direction of elevation and orange in the direction of azimuth, we see that the drift showing up, right? So one of the metrics that we're trying to use here is the best linear line fit to the data and versus different speed. As you can see, the faster they're walking, the more steeper that line of the error is going to be. Another one is the jitter, which represents the wobbling or the standard deviation of the zero mean error for us, which is another important feature in order to make sure that the quality of the data remains valid. If we jump into the results, here you can see that for different speed values, we see the drift result for hard rig and soft rig shown in each row. The hard rig shows a larger value of drift compared to the soft rig, and that's probably because of the weight and the way that it rigidly sits on the face. However, in contrast, the soft rig provides us with a larger value of jitter, which makes sense mechanically and ergonomically. The way that it sits on the face is a little bit smoother and less rigid. Therefore, we can see that each of these two devices are providing us with kind of different properties. So in summary, in this study we were able to see that there's a compromise that needs to happen between these two different rigs with respect to drift and jitter. And the other observation is the more rigidly the device sits on participant's face, the more error in the gaze we're going to have in time. As a future direction, here I'm showing you the scatter plot of target versus gaze At the end of each validation session, the 15-point grid that I mentioned earlier, and we can see that the drift is kind of showing itself and the pattern of the way that the gauge tracking deteriorates in time. The hope is in the future to use this information and also the information about the eye images in order to correct for the slippage and basically resolve this problem for active observer. Toward the end, I just want to thank the organizers and also my advisor, Dr. Paul McNeilage, our collaborator, Dr. Michelle Green, and graduate students. Without them, this study wouldn't be possible: Broth, Brian, Christian, and Sabi. Thank you for your attention, and I would be happy to take any questions.